In this lecture we study the normal probability model, where the random variable follows a normal distribution. So, we first try to understand the normal distribution. So, normal random variables have bell shaped histograms. All of us have seen the bell shaped curve. We will also be showing the bell shaped curve in this lecture. The probability distribution of a normal variable is the bell curve. The probability of distribution of any random variable, that is the sum of enough independent random variables, is also bell shaped. We will see that. If random variables to be summed have a normal distribution, then the sum has a normal distribution. Sum of just about any random variable are eventually normally distributed. So, if we take a random variable and keep summing them, we at some point would come to the normal distribution. So, you have seen 2 or 3 sentences, and we will try to explain these sentences suitably. For example, you consider tossing a coin 10 times and compute the probability of 0 heads to 10 heads. So, p is equal to 0.5 and n is equal to 10, and we realize that since p is 0.5, probability of success is also equal to probability of failure, and therefore p of 0, which means probability of getting 0 heads, assuming head is a success, can be calculated by NCx p power x q to the power n minus x. Q is 1 minus p, we have seen that in the previous lectures on binomial. So, p is also equal to q, therefore p of 0 is NC0, which is 1, p to the power 0, 0 heads, and q to the power 10, and since p and q are equal, you would have p to the power 10 in all these cases, except the NCx will change. So, probability of 0 heads will be equal to probability of getting 10 heads, which is equal to 0.0009766. Similarly, probability of getting 1 head will be equal to the probability of getting 9 heads. Please note, in this case, because p is equal to q, this happens, and both are equal to 0.5. So, 0.009766, p of 2 is equal to p of 8, 0.044, p of getting 3 heads is equal to p of getting 7 heads, which is 0.117, p of 4 is equal to p of 6, 0.205, and p5 is 0.246. So, if we add from p of 0 to p of 10, we will get 1. So, this comes from the binomial distribution doing it, and if we try to plot this, we try to get a picture which is like this, which is very similar to the normal curve. So, the central limit theorem, which is a very important theorem, says the probability distribution of a sum of independent random variables of comparable variance tends to normal distribution as the number of summed variables increases. So, try tossing the coin as n tends to infinity, we will get this. Now, what we will look at more in this lecture is the standard normal distribution. We will study this further. There are some more equations that describe the normal distribution, which we would possibly not do in this introductory course on probability and statistics. Perhaps the first level course we would look at all of that. This is the normal distribution curve, or the bell shaped curve. This is also the standard normal, we will also see the difference. A typically standard normal distribution has mu equal to 0 and variance equal to 1. Area under the curve will be equal to 1. So, in otherwise you would have a mu here, now we have 0 here. Now, also realize that this does not touch the x axis from either side, it kind of asymptotically converges, it just goes on and on. Therefore, in principle the random variable can take any value. Now, remember that both the normal curve as well as the standard normal curve look similar, the shape is the same, except that we have mu equal to 0 in the standard normal and the corresponding mu in the normal distribution. We will see examples to understand all of this. So, which of the following can be treated as normal? So, whenever the normal comes, one has to understand this symmetry, one has to understand the peak in the middle, and so on. So, when we plot, so what kind of a curve can we get, and from that curve can we say that something is normal. So, simple characteristics are the random variable can take any value, there is a peak at mu, and then it is a bell shaped curve, and then there is a symmetry. So, we will look at all these factors and try to answer these questions. Marks obtained out of 100 by 200 students in a subject. Generally, we could look at this kind of as a normal distribution, in the sense that there are some interesting reasons as to why we need not, because we just saw that the mark, if we assume it to be normal, it can take very large value, it can take a very small value as well. But then when we are talking about an exam in a subject, we have clearly defined boundaries, let us say 0 to 100, and therefore we do not have a value of x equal to 1 over 1 and so on. But in spite of that, we could expect a reasonable amount of symmetry, and we could think of this as close to a normal. Money value of each purchase in a supermarket in a day may not be close to normal. What will happen is the average, it will not peak at the average. We could have few very large purchases, we could have a large number of small purchases and so on. So, it could be a skewed distribution. So, a skewed distribution would not be symmetric. We have seen skewed distributions or skewed distributions earlier in this course. So, it will taper to the right, the peak will shift, will be to the left if it is right skewed, and the other way if it is left skewed. Career scores in ascending orders of a cricketer, it talks about individual scores. So, we would not be able to do that, but if we sort these career scores in some order and try to build a histogram and so on, so one might try to get a picture that is reasonably close. But again, in this case there will be a small number of very large scores and a large number of small scores. So, we could expect some amount of skewness in the data, and therefore, we need not treat it as close to normal. Number of visitors in a day to a department again may not be very close to normal. We could have some days you could have simply a bunch of visitors, we could have 40 or 50 visitors on some days, and on some other days we would have a small. So, we will have a large number of days with small number of visitors and small number of days with a large number of visitors, and therefore would not be close to normal. Now, what is the relationship between the normal distribution and the standard normal distribution? So, we will be working with the standard normal distribution most of the times. So, a given normal distribution will have a given mu and a given sigma. The standard normal changes that to mu equal to 0 and variance equal to 1. So, what is the difference? So, what is the difference is here? Z score measures the number of standard deviations that separates a given value from the mean. So, if mu is the mean and sigma is the standard deviation and x is a given value, we calculate what is called x minus mu by sigma. So, x minus mu is the difference, divided by sigma is the difference divided by the standard deviation, which tells us the number of standard deviations that separates the value from the mean. For example, if z equal to 2, then x minus mu is equal to 2 sigma. Therefore, the number of standard deviations that separates the value from the mean is 2. So, z is x minus mu by sigma. So, quickly to do a computation, average mark in a class of 200 students is assumed to be normal with 60-20. So, mu is 60 and standard deviation is 20. Find the probability that a randomly chosen student has mark greater than 70. So, we first find out z. So, in this case we normally use small z, lowercase z. So, I have shown it with an uppercase z here, but we use z is equal to x minus mu by sigma. Mu is 60, sigma is 20, x is 70. So, z corresponding to x equal to 70 is x minus mu by sigma, 70 minus 60, which is 10 divided by 20, which is 0.5. So, probability of x greater than 70 is the same as probability of z greater than 0.5, because we have now reduced or approximated or converted the given mu and sigma into a z score, and we will start working using the z score and using the standard normal table and the z score, the area would correspond to the probability. So, what we have to understand is, given mu and sigma, x is related to z and z is equal to x minus mu by sigma. So, for a given x we can calculate z and then for the z value get some figures from the standard normal and then use it to solve for the given x. That is something which we will do. From standard normal tables the area we will compute and show. So, there is the standard normal table and the area under the standard normal table, we will use that area to compute. Now, how do we do that? I have just shown these two tables courtesy the internet. So, I acknowledge that, and these tables are available in open source, these tables are available in most statistics books and it is not difficult to get these tables. You will see a clutter of numbers and sometimes you will see a small picture which also tells you what this number represents. Now, in this table the picture is replaced by a sentence which is table values represent area to the left of the z score. So, if you read this table very carefully, since I have to show the entire thing in one slide, I had to reduce the font size. So, you will not be able to read it. So, I am reading it for you. Table values represent area to the left of the z score. So, what is it? So, there is a z score here, it starts from minus 3.9 and goes to 0 in this picture or table, and you also see 0, 0, 0, 1, 0, 2, 0, 3 and so on. So, if your z score is minus 3.43, I am just placing the mouse in that place, minus 3.43. So, area to the left of z equal to 3.43 is here and that is 0.0003 is the area, 0.0003 is the area to the left of minus 3.43. Now, we go to the next table which is also a similar table, again area to the left, and then we realize that here z varies from 0 to 3.9 on this and then we have z on the other side. So, if we look at plus z is equal to plus 3.25 let us say. So, 3.2 is here, 3.25 is here. So, 0.99942 is the area to the left of 3.25. So, if we use these two tables, what we understand is given a z value, these tables give us area to the left of the given z. Since the total area under the normal standard normal curve is 1, area to the right of the given z will be 1 minus the area to the left of the given z. So, we will use this to solve some of these problems. So, now what did we do here? So, somewhere here we said now we have to find out what is the area for z equal to 0.5. Before we do that, let us also understand something from the two tables. If you see carefully from the two tables, you realize that z equal to minus 3.9, it is coming to z equal to 0, and then you realize that z is equal to, now if you have to see this a little carefully. So, we see z equal to 0.00, the area is 0.5. So, z is 0.00 is this point, this is z is equal to 0. So, z is equal to 0.00, the area to the left of this, which means starting from here right up to this curve, right up to this point, bring it down, this area is 0.5 which we know. Now, let us try to understand, because these values are coming and increasing this way. So, what is this? So, this is minus 0.09, this is 0.08 and so on. So, you realize that minus 0.09 will be very close to 0 here, and 0.08 would even be slightly to the left of this and so on, and then we realize that the values are actually approaching 0.5. So, at z is equal to 0, the area is 0.5. If you look at the next table, once again z is equal to 0, the area is 0.5, and as we keep increasing z, the area to the left of it keeps increasing, and you realize that at 3.99 the area is 0.99997, So, that is where this 3 sigma becomes important. So, if x minus, remember z is equal to x minus mu by sigma. So, when z is 3, then x minus mu is equal to 3 sigma. So, the area under the left of 3 sigma is 0.99997. So, roughly your 3 sigma will be somewhere here. So, this will be z equal to 3. So, almost the entire thing is covered. So, as now x increases beyond this and goes even to a very large value, the area to the right of it will be negligible and will be close to 0. So, generally we would be looking at z equal to plus 3 to minus 3, and plus 3 effectively covers the entire bell shape of the standard normal and has area almost equal to 1.99997 and so on. So, now let us try to find out what is the value for z equal to 0.5. So, for z equal to 0.5 we look at this table. So, z equal to 0.5 is here. So, 0.5 is 0.500, therefore 0.691 is the area. So, 0.691 is the area. So, from standard normal tables, area for z equal to 0.5 is 0.691. So, we are now interested in z greater than 0.5, which means to the right of z is equal to 0.5. So, let us take it as 0.69 for the purpose of discussion. So, area to the left of z equal to 0.5 is 0.69 and area to the right of z equal to 0.5 is 0.31, and therefore, the probability that a randomly chosen student has a mark greater than 70 is 0.31. So, let us actually look at this again. So, you could have z equal to 0.5 somewhere here and we would have this somewhere here. So, to the left of this is 0.69, to the right of this is 0.31, and therefore, the answer is 0.31. It is also important to note that we do not try to answer a question like what is the probability that a randomly chosen student has a mark equal to 70 using this kind of analysis, which becomes very difficult, and much later we will know that such a probability tends to 0 and so on. But as far as the course that we are doing is concerned, we restrict ourselves to finding out what is the probability that somebody has mark greater than 70, what is the probability that somebody has mark less than 50, what is the probability that somebody has a mark between 30 and 40. So, all these questions can be answered, but we do not try to answer a question what is the probability that the student has a mark equal to 70 or equal to 80 through this kind of a analysis. So, this is how we relate the given mu and sigma to a z score and then use the standard normal table to try and answer questions like what is the probability that mu or x is greater than 70 or z is greater than something. So, for a given x we find out a z score and then area under the standard normal curve helps us to find out the probability. So, let us for example, for the same problem which we were discussing. So, you realize that this is z equal to 0.5. So, from the table area to the left of it, that is starting from here going right up to this, coming and touching this point, come down and here, that area is 0.69, and therefore, area to the right of z equal to 0.5 is 0.31, which is the answer to the given question. So, we will continue and take some more examples to understand the standard normal and have a discussion on it. Now, we look at this match the following. There are 5 items in column A and 5 items in column B. So, mean of x, variance of x. So, mean of x is mu, variance of x is sigma square, probability of x above one standard deviation greater than the mean, probability that x less than equal to mean, and probability of z score less than 1. Probability of x less than equal to mean. So, x equal to mean is z equal to 0, x minus mu by sigma. So, when x is mu, z is 0. When z is 0, it comes in the middle of the bell shaped curve. So 0.5 is the answer. So probability x less than mean is 0.5 for the fourth one. Probability of x above 1 standard deviation greater than the mean. Actually, if we go to the normal tables, we find that it is area to the left of z equal to 1. 1 standard deviation greater than the mean is z equal to 1. So area to the left of z equal to 1 is about 0.84, which we approximate to 5 by 6. Therefore, area above 1 standard deviation is 1 minus 5 by 6, which is 1 by 6, which is given here. And for question number 5, z score less than 1 represents area to the left of z equal to 1, which is about 0.84, which is approximated to 5 by 6 in this, and therefore the answers are mu for the mean, sigma square for the variance, above 1 standard deviation 1 by 6, less than equal to mean 0.5, below 1 standard deviation or z less than 1 is 5 by 6. So let us look at some more questions. So let us assume that age of 1000 employees in a factory has mean equal to 40 and standard deviation is equal to 10, and to answer these questions we are trying to assume that it is normal. So when we make this normal assumption, one has to keep in mind that x can take a very large value or x can take a very small value, but then we are going to make this normal assumption and then try to answer these questions. So more employees are older than 45 than between 35 and 45. So mean is 40, standard deviation is 10. So if we take 45, then z is equal to 45 minus 40 by 10. So z is equal to 0.5. So area to the left of 0.5 we just now saw is 0.69, and area to the right is therefore 0.31. So more employees older than 45 is probability is 0.31, and between 35 and 45 is the difference between z equal to 45 and z equal to 35. So z 35 is minus 0.5. So when z is minus 0.5, one has to understand that the area to the left of it is 0.31. Therefore, the required area is 0.69 minus 0.31, which is 0.38, which happens to be greater than 0.31. So let us try to understand this a little bit more. So let us say we have this. So this is a case where age is 45, so z is 0.5. So if we look at a case where age is 45, which is 0.5, so this area to the left is 0.69, this is 0.31. So when we look at 35, z is equal to minus 0.5, which will come somewhere here, it will come somewhere here, and by symmetry this area will also be equal to this area. So area to the left of z equal to minus 0.5 is 0.31. Area to the left of plus 0.5 is 0.69, and therefore the area between these two is the difference which we saw here as difference between 0.69 and 0.31 is 0.38, which is greater than 0.31. Therefore, more employees between the age group of 35 and 45 than employees with age greater than 45. Most employees are older than 30. Now the mean is 40, so z is minus 1, and because z is minus 1, the area to the left of that z will be less than 0.5 and area to the right of that z will be greater than 0.5. Therefore, we will have more people older than 30. In fact, the average is 40, therefore we will have more people greater than 30. How many more we can find out? So z is equal to minus 1, which gives us area to the left is 0.16 from the table, and therefore to the right is 0.84, therefore 84% of the people would be older than 30. If the ages are represented in months, would it still be normally distributed? Yes. So multiply the random variable by a constant, it will still be randomly distributed. If the original one is, the mean will only change. If the employees retire at 60, how many do you expect to retire soon? Is an interesting question. So when x is equal to 60, z becomes equal to 2 and area to the left is 0.98. So, 2% will be over 60 is the actual answer, but then we have to go back and realize that we have made that normal approximation. So, these two people we now say would either have retired or would say very close to retirement, but 2% will be over 60 and therefore, they would have retired by now if 60 is the retirement age. If employees below 30 years are sent for training, how many would you expect to go for training? So, we have already seen that when age is 30, z is minus 1 and area to the left is 0.16, therefore, 16% of the people would be going for training. If employees above the age of 50 have to go for a health checkup, how many do you expect to go? So, when x is equal to 50, z is equal to 1 and we know that area to the left is 0.84. So, people with age less than 50 is 84%, people with age greater than or equal to 50 will be 16% and these 16% will go for a health checkup. So, now you see how a normal approximation can help understand certain things in reality. But one can question the normal assumption in this case, but let us assume that we have made that assumption and we have tried to answer these questions. So, if x and y are both normal with mean mu and standard deviation sigma, would the distribution of 2x, 2y and x plus y, how would it look like? So, all of them will be normal with mean 2 mu, but since variance is additive, the variance of the sum will be 2 sigma square and not 4 sigma square. Therefore, standard deviation will be root 2 times sigma and not 2 sigma. The average salary in an office with 2000 people is 20,000 with standard deviation of 10,000. If the salary is normally distributed, how many would have salary greater than 50,000? So, when x is 50,000, x minus mu by sigma is 3. So, z is equal to 3. Area to the left 0.999, area to the right is 0.001. So, 1 in 1000 would get a salary greater than 50,000. If all of them get a bonus of 5,000 for a festival, what happens to mean and standard deviation? So, the mean increases, so 20,000 will become 25,000, standard deviation will be the same. If all of them get a 10% increase, what happens to mean and standard deviation? 10%, so multiplied, so both mean and standard deviation will increase by 10% in this case. Find the probabilities from standard normal tables, z less than 1. So, we already saw that z less than 1, area to the left is 0.84, so the answer is 0.84. So, question number 2, find the probability of z greater than minus 1. So, we know that z equal to 1, area to the left is 0.84, z equal to 1, area to the right is 0.16. It is symmetric, therefore, z equal to minus 1, area to the left is 0.16, which is less than z equal to minus 1. Therefore, z greater than equal to minus 1, the answer is 0.84. Probability of mod z greater than 1. So, mod z greater than 1 means it is either z greater than 1 or z less than minus 1. So, when z is greater than 1, mod z is greater than 1. When z is less than minus 1, for example, when z is minus 2, then mod of z is 2, which is greater than 1. So, we have already seen z greater than 1 is 0.16 and we also know that z less than minus 1 by symmetry is 0.16 and therefore, what we want here is z greater than 1 and z less than minus 1. So, 0.16 plus 0.16 is equal to 0.32. The fourth one is z is between minus 1 and plus 1. So, z equal to 1 has 0.84, the mean is at 0.5. So, between z equal to 0 and z equal to 1 is 0.34. Between z equal to minus 1 and z equal to 0 is also a 0.34. Therefore, between minus 1 and plus 1 is 2 times 0.34, which is 0.68, which is what we show through these pictures. This is roughly z equal to 1. So, to the right is 0.16, to the left is 0.84. So, this is 0.16, this is 0.34, this is 0.34, this is again 0.16. So, you realize that this two put together gives us 0.68, this and this gives us 0.32 and so on. Now, there is an investment of 200,000, it is expected to grow by 15% with a standard deviation of 25%. What would be the change in value if we rule out the worst 2%? So, when we have this worst 2%, so for area to the left of 0.02 for the worst scenario, so for area equal to 0.02 which is the worst 2%, z is minus 2.05. So, the worth can reduce up to the point of z is equal to minus 2.05. So, mu plus z sigma will be the value of x, because z is equal to x minus mu by sigma. So, x will be mu plus z sigma, which can go to minus 36.25%. So, which would give us a loss of 72,500. What would be the expected return if the loss is 20%? So, mu minus z sigma is minus 20, and then we get a certain value of mu. So, mu is 2.05 into sigma is minus 20, so we get this certain value for mu. If the period of investment is doubled, would the loss double? No, risk becomes smaller as we move along with longer times. Therefore, if the period of investment is doubled, we also realize that the standard deviation does not get doubled. So, the risk becomes smaller as we increase, and therefore, the loss would not double, the loss would be less than double the value. So, this is some examples to study the normal distribution, to understand the standard normal table, to understand the z values, and to use them to solve some simple problems with the assumption of the normal distribution.